Okay, in this lecture, I want to talk further about the general framework for plasticity in 3D. Reminding you, we've already talked a little bit about the yield function. I want to talk about something called the consistency condition, and it's actually something that you've already seen. I just didn't define it in that way for you. So, to kind of build up to what the consistency condition is, and also to kind of frame why we can use it to talk about the evolution of plastic strain and other internal variables. Actually, let's just begin by reminding you of what the yield function is. So recall that during yielding. So recall during yielding. Okay, we have that the yield function f, which we said was a function of the stress and some internal set of variables q. Remember that in the internal variables could just be the plastic strain, or they could be additional variables as well. Okay, so sometimes we'll break out plastic strain separately, other times we'll leave it included. But during yielding, that yield function equals 0. And furthermore, if we're yielding, we had an additional condition which basically said we wanted to know if the additional increment of stress tended to cause the yield surface to grow, or if we were unloading, or if we were running along the yield surface. And so we said yielding only occurs if partial of f with respect to sigma times d sigma is greater than 0, right? Those were our conditions. And we said in the previous lecture that this quantity del f del sigma times d sigma, that's actually part of df, right? The differential there, okay? So, and we also said that we know that during loading f always equals 0, so that, so let's write that down. During loading, plastic loading, how about? Okay, so during plastic loading, the f of sigma and q always equals 0. Okay, so that means that during the plastic loading, no matter what happens, that the differential change in f during loading must also equals 0. So that's an important condition. Or we could write it in rate form. So, or in rate form, we can write just with the dot there. We could say that f dot, and I guess maybe I could put that that's still a function of, well, we'll just say f dot equals 0, right? So either of those essentially mean the same thing, and this requirement is what's known as the consistency condition. So this requirement is called the consistency condition. Consistency condition. Okay? So remember that. So let's go ahead and how about we restate it? So let's restate for the general case where f is a function of sigma and q, right? So let's just write out what df equals, right? Go back to Calc 3. We have some partial derivatives, and we do the chain rule. We have that partial of f with respect to sigma times d sigma plus partial of f with respect to q times dq, and that's actually a dot, is going to be equal to 0. Okay, if you prefer index notation, then we could write this as partial of f with respect to sigma ij, d sigma ij, plus the partial of f with respect to, let's say, qk dqk. equals 0. Okay, so this kind of illustrates what we were talking about in the last lecture. During yielding, we said this quantity must be greater than 0, right? Which then implies that this quantity here, partial of f with respect to the internal variables times the increment in internal variables, that quantity must be then less than 0, or else we can't get to 0 there. Okay? So we could just rearrange this equation. So rearrange the above. And if we do that, we end up with that the partial of f with respect to sigma ij, d sigma ij, is equal to negative partial f with respect to qk, dqk. Okay? So, well, that feels like an exercise in futility, maybe. So what does that actually tell us? Why would we write this? Well, what this says is we know that that this is greater than 0. So is it possible for this to be greater than 0 if this is equal to 0? Of course, the answer is no. The only way that we can get the correct answer, having this be greater than 0, is if dqk is non-zero. In other words, plastic deformation can only occur if the internal state vector, which we represent by q, if that vector changes during plastic deformation. So let's write that down. So plastic deformation can only occur. If the internal state variable, we'll call it Q, changes during deformation. Okay? So that's what that equation tells us. Okay? That suggests then that we could introduce a relation between the plastic strain that we get and the internal state vector. Okay, so that's why we wanted to make that statement. So it suggests that we can write a relation. So we can write a relationship, if you like, between the plastic strain, epsilon p, and the internal state vector q. Okay, this shouldn't be too surprising. What we did here was just prove it, but it shouldn't be too surprising because the internal state vector might just be the components of the plastic strain tensor. So if the plastic strain tensor, let's say, has 6 unique components, Q could just be a vector that has length 6 that contains each of those components. So that there exists a relationship shouldn't surprise us, but potentially there's more internal variables than just the plastic strain that might drive the plastic strain. So what we would end up writing is if we believe that we can do this, which I hope makes sense now, then we would write that the increment of plastic strain, the epsilon ij plastic, is going to be equal to, and we'll just call this term Hij, and this is actually, I'm going to put a superscript k, which is an index here, times dqk. Okay, or in rate form, if you want, we can write that as epsilon ij plastic dot going to be equal to Hij k times q dot k. Okay, those are equivalent statements, and let me just say we need to define what this H term is. And H, it's actually not a third order tensor like you might think. It's an array of second order tensors. Okay, so an array of second order tensors. Okay? The other thing I'll say about this is that there's no requirement here that those be constant. So So they're not required to be constant. Not required to be constant. Okay? So hopefully that makes sense, that we can link those two. In the event that, let's say, Q is just the internal state vector, in the event that that only contains the plastic strains, then these second order tensors represented by Hij are just going to be essentially zero tensors except for one component potentially in that 3x3 array. Okay? Okay, so that hopefully is straightforward. Alternatively, we could think of the plastic strain increment as just simply a function of the stress, the internal state vector Q, and then whatever the increment in stress is. So I'll say alternatively, you could write the functional form of the plastic strain tensor. So write the functional form for, let's say, the increment, d epsilon p, the plastic strain tensor increment, as follows. We could say it's, well, d epsilon ij p is going to be equal to some, whatever that function is. D epsilon ij p is a function of sigma q, the vector, and then d sigma. Okay? And then we could, if we can do that, and that's hopefully pretty obvious. And remember that epsilon ijp is probably the least. That's the least internal state vector you could have. Again, you could have more, but if we had other internal variables represented by q, they could be represented similarly. So let's just say that similarly, you can represent the other internal variables. Okay, so other internal variables, oops, that's supposed to be variables, Q, in the same way we could say that dq is equal to, is a function such that we have sigma q and then d sigma, right? Hopefully that's straightforward. Okay. Now I have to invoke an experimental observation. Okay, so in this experimental observation, so let's write that down. Experimental observation. Okay, and in this experiment, when Q, the internal state vector, was just taken to be the plastic strains, Okay, so we could write, if you wanted to, that Q, if we wrote it in row vector format, would look like epsilon 1, 1 plastic, epsilon 2, 2 plastic, epsilon 3, 3 plastic, epsilon 1, 2 plastic, epsilon 1, 3 plastic, and then finally epsilon 2, 3 plastic. Okay, so that would be, when we take Q to be that, what we find, or what was found, is that the plastic strain increment d epsilon ijp is always orthogonal, right, to the yield function surface. Okay? I'll draw a picture of that here in a second. So it's always orthogonal to the yield function surface. We know that that yield function surface is completely defined, so which is completely defined, right, by sigma and Q, right? That yield surface does not depend on the stress increment. So let me see if I can draw a picture a little bit of what that means. So if I have a, here's my stress, or actually it could be a strain axis, right? There's nothing that says my F has to be defined in stress space. But let's do what we had done before, sigma ij, and then I'm going to write that this is, could be epsilon ij plastic as well, could be that axis, right? You could write potentially this yield surface as a function of epsilon ij as well. But anyway, let's go ahead and draw this. I'm obviously drawing in 2 dimensions, but it's a yield surface. And we'll start here. We have some value. This is a location. Let's say we're on our yield surface, and maybe that is our d sigma. Okay. What was experimentally observed is that if we were to look at d epsilon plastic, it always ended up being orthogonal to the yield surface. So let's say that in a different way. It says that the direction of d epsilon ij plastic, or also we could say the direction of dq, the incremental change in the internal state vector, did not depend on the direction of the stress increment. Okay, did not depend on the direction of d sigma ij. Okay. It's the only thing we needed to know was that only if d sigma ij indicated yielding. Okay, so if it satisfied that del f del sigma times d sigma, if that quantity was greater than 0 and it satisfied yielding, then we can draw, let's say, our stress increment, but but the direction that we increment that does not control the increment of the plastic strain direction. Okay. Okay, so based on this assumption, which again I will say was only done when the plastic strain was the internal variable, and what this assumption that we're about to do will extend to all internal variables. So it's not a proof; it's just an assumption in the model. But let's just say based on the experimental observation. So based on the experimental observation, it's commonly assumed. Commonly assumed. Number one, it's assumed that the magnitude of a dq, so how much it moves, how much the internal stress vector changes during any given stress increment, that magnitude is a function of stress, the internal state vector, and d sigma. So let's write that down. So the magnitude of dq, and you could also, if this is the case, we could say also d epsilon p, so the plastic strain increment, is a function of sigma, q, and the stress increment d sigma. Okay? But per that observation, remember we just talked about that the direction of dq is not dependent on the stress increment. So we would write that the direction of dq is only a function of sigma and q, right? That's uniquely defined. Once that defines the yield surface, we know the direction that dq is gonna go. Okay, so why do we care about that? Well, so we've now basically broken the evolution dq up into a magnitude and direction, and they have different functional relationships. So we can write, I'd say simplify, but it's going to seem confusing at first. So then we can write dq is going to be equal to b times the vector t. Or you could write it as dqk is equal to b times tk, right? Those are equivalent. What's tk? It's a vector valued function that defines the direction, okay? So tk, which is a function of only sigma and q, right? It's just a direction, is a vector valued function right? It's a vector valued function that gives the direction of the change in the state vector and the internal state vector. Okay, and B is a scalar function of sigma q, and now also the stress increment d sigma is a scalar valued function put a hyphen there too. Scalar valued function giving the magnitude of the change. So one is direction, one is magnitude of the change to Q due to some d sigma. Okay? So the question that we want to talk about in our next lecture, then, now that we've defined it this way, the question we want to answer is, how can we define B and T? So B and T, right? And because if we have to do that if we want to ultimately get to the flow rule. So that'll be the topic of our next conversation. But I wanted to introduce, first off, the consistency condition and how we use it to sort of break down the internal state variable evolution, which is also related to the plastic strain evolution, into these two parts of magnitude and direction. Okay?